I'm going to finish by a very important topic, multiplying A times B. Oh, look, a clean board. So now I want to multiply a matrix by a vector. Okay, everybody knows how to do it. You take a row of A, so you take a row of A, and you take a column of B, and you take the dot product, so you get dot product. Row dot column, row dot column. That's, again, low level, like okay for beginners. But we want to see that matrix multiplication AB in a deeper way. And the deeper way is columns times rows. Columns of A, rows of B. Columns times rows. Oh, we had a column times a row. Right? That was this rank 1 example. We had a column times a row, and it produced a matrix, and that's what it looked like. And its rank was 1. So those are what we have. So it's a combination of. It's very like AX. I'm really just extending the AX idea to AB. So this is the old way. The new way is columns. So there's column K. It will multiply. Sure enough, it multiplies row K. Everybody sees that it will happen that way. If you do it the old way, when you do a dot product of something here, you're doing these multiplications, and when you hit column K here, you hit row K there. So these are connected. So I get things like column K of A times row K of B. And I don't know what notation to use, so I just wrote the words. Okay. But now that's one piece of the final answer, AB. That's a rank 1 piece. That's like a building block. So I add from K equal 1, column 1 times row 1, column 1 of A times row 1 of B, plus da-da-da, plus column K, plus, and of course, I stop at column N of A times row N of B. So it's a sum of outer products. Sum of, so everybody sees a sum because I have column 1 times row 1, column K times row K, column N times row N. And then I add those pieces. It's just the generalization of AX to a matrix B there. So it's the sum of column K, row K of A, row K of B. And maybe we check that gives us the right answer, or maybe I won't do that here, but it's all we're doing is the same multiplications in a different order. Actually, let's just quit with 1 minute. We can figure out how many multiplications are there. How many multiplications to do a M by N matrix A times a N by P matrix B? So that's A times B. How many individual numbers, because this would determine the cost of it, how many numbers would we need? Well, suppose we do it the old way by inner product, row times column. So how many multiplications to do a row times a column and get one entry in the answer? N, right? The row has length n, the column has length n multiplications. So that's n, and now how many of those do I have to do? MP, because what's the size of this answer? The size of this answer is m by p. Okay, so if I do it in that old order, like n multiplications to do a dot product, and I've got this many dot products in the answer, So I've got MNP multiplies. Now, suppose I do it this way. How many multiplications to do one of those guys? To multiply a column by a row. To multiply a column by a row, this is a m by 1, and this is a 1 by p. One column, one row. How many multiplications for that guy? MP. And how many of those rank 1s do I have to do? N. You got it? It's MP times N. Now, it's the other way was N times MP. So it gives the same answer, MNP multiplications. In fact, they're exactly the same multiplications, just a different order. Okay, we're at 1:55. Thanks for coming today. I'll talk more about the class and about linear algebra on Friday. Thank you.